First of all, I heard my voice, therefore it's a little bit strange. I hope you can still understand me okay enough. If not, just ask back. So, yeah, welcome to today's final workshop of the DEcent project. It was a very interesting project where we had the corona in the middle of that. And anyways, we have great results, and therefore I'm really happy today that we can present the results to a little bit bigger audience and showcase a bit what we did in the past 3 years. On this slide, we see the project duration, and we also see the partner logos and, of course, our funding organizations, so the Federal Ministry for Economic Affairs and Energy and Business Finland. So thanks to them, and also a big thanks to the PTJ. Fabio Lenzner is here with us today for the great management of the project. It was really a pleasure working with you. Thanks a lot. So for today, we have the following agenda planned. So we are in the middle of the welcome, and afterwards we look at the use cases and the system architecture. Then we look at the identified challenges and solutions, starting with the IoT substrate interfacing the hardware and the example of a battery. Then we look at AI for modeling and optimization of the energy exchanges, and local management. Then we look at the trading agent, a central component of our system and the value forming across multiple markets. Then we look at market and market clearing and mechanisms related to that one as a central mechanism for exchanging energy. And finally, we look at security enablers as a last building block that will be showcased today there. Then at 3 o'clock, we have planned to show a demonstration of the co-simulation that I will also mention in the project description that will just follow. And then we have the results on dissemination and communication, and the closing at 3:30. So we have 2.5 hours of highlights ahead of us. As it's really long, when you have questions, don't wait until the end. Just ask the questions right away when the questions come. Okay, good. So everything started with the Förderbescheid. So this was in August 2018 on the German side, and from that on, it went fast. So we had very nice project meetings at the different partners as planned. And I especially wanted to show the pictures here because projects are always about people. And this project was particularly nice because we really created a very nice group. And it's a big pleasure having worked with all of you. And therefore, I'm a little bit sad, of course, that the project is ending. On the other hand, I'm very happy that we achieved such great results that we will be presenting today. Okay, so 2019, everything was still okay, and then 2020 came, and the global COVID-19 pandemic that nobody anticipated before, and of course, this was the end of our physical project meetings, but nevertheless, we coped very well because we had then virtual meetings, but of course, this made it more difficult because we were especially in a phase there where we wanted to do integration workshops of the different partner technologies in the joint demonstrator. This became more difficult, but as we will see today, we still managed, the team managed to create a great virtual demonstrator nevertheless and achieve wonderful results. At the end, after October 2020, I just put multiple pictures because we really had a lot of meetings for organizing the demonstrator, getting results, and so on. So what was the goal of the project? So the project was very timely and even is still timely because it's still a super hot topic. It's about, we have neighborhoods. In the neighborhoods, we have decentralized energy consumption and production. And how can we use ICT to leverage the effect of locally using energy for different positive effects like resilience, energy saving, and so on. And that it was timely also came with seeing that there came a little bit publications in that directions. There were projects that were also going in that direction. And so it was very nice to see that we were really at the forefront of what was currently done in the research domain. The idea of the project was to have a virtual smart neighborhood as central entity in the project. and around that develop different aspects, of course, technical solutions, but also business models and legal recommendations. The smart neighborhoods that we had in mind are these that we have here, and I'm very happy that in the project, through the different partners, we had also physical neighborhoods, so real houses with real data, through partners in Germany and through partners in Finland, that we could use then as co-simulation in the virtual joint demonstrator site. I just quickly want to remind us on the objectives, not going into detail. So we wanted to look at how can we enable cross-commodity energy management. We wanted to look at how can we have real-time secure integrated management of this energy based on the infrastructure shown before. We wanted to look at how can machine learning, AI technologies for adaptive cross-commodity flexibility management help us to find solutions there. How can they help to have better effect of the methods that we were developing? We looked at blockchain and smart contracts for connecting these households in the smart neighborhood. We looked at business models, so how can value be taken from such an infrastructure that is not yet present today? We looked also at, okay, what are inhibitors that are currently there from the policymaker side that make it difficult to implement something like that, and which ones would be good to change maybe. And finally, the joint asset, as shown before, was the virtual smart neighborhood that enables the piloting of the tools and the mechanisms that we will see later today in the presentation. The work plan was as follows, with the most important thing being the iteration at the bottom. And due to the corona, this did not go as we had planned originally, with lots of meetings and so on, but instead virtually. Therefore, it was good that we virtually wanted to connect all this, because it a little bit was in our plan already. But anyways, it would of course have been much nicer to meet the people and work much more on that. Okay, so without further ado, I just wanted to briefly recap the project setting, and that brings me and us directly to the second part. And I hand over to Fortiss and VTT for the use cases and system architecture.
Okay, then how we start in the project. Initially for that kickoff meeting, we had a small session on use cases, and out of those use cases, we also make up our minds about the possible system architectures. And this is what the second presentation slot will be about. So initially, Markus Duchen from Fortiss, will introduce what we have done for the use cases for the virtual neighborhood. So as software architects, we classically started with setting up user stories, as I said, in the frame of a short workshop. We had also during our kickoff meeting, and we came up with 20 short user stories. So as somebody, I want something so that I have a benefit out of it. And during the first couple of weeks and the first month, we generated out of those 20 user stories, 9 use cases with appropriate descriptions and different workflows, and also boundary conditions and acceptance criteria for the 4 main stakeholders we identified. So operators, some service providers, also participants within that virtual community, and also for the policymaker, who also has a certain interest in stable networks. Out of those 9 use cases, we identified 3 to be the most relevant, and which we also tried to implement, and also implemented within our virtual demonstrator. And those are of course, sharing and trading of electricity and heat, the integrated energy, since we want to share electricity and heat. Of course, also sector coupling, cross-commodity energy was also in the title of our project. So this is also a quite important use case within our project. And of course, as Mark Oliver also introduced in our objectives, energy management systems with AI-based decision making in order to really participate at those envisioned market we had in mind when building those virtual environments. Those three main use cases are also located in the project plan we just saw. So the AI energy management system really deals with the IoT secure data handling as well as AI for adaptive flexibility management. So relating mostly to work package or tasks we conducted in work package 3. The trading and sharing of electricity also is related or closely related with market mechanisms, which are implemented within smart contracts from the blockchain perspective, and also for the business models and the analysis of that market. And the integrated energy use case, of course, deals with sector coupling or cross-commodity framework we are trying to build with electricity, heat, cooling, transport, and in future, most likely also other sectors which will be integrated here. And this was a short overview on the use cases, how we started, and how we initially made up our minds. And now I'll hand over to Jussi Kleander in order to present the system architecture.
Okay, thanks, Markus. So the next step in the project after the use cases was to design the system architecture for the decent and mainly for the ICT enablers we were researching and developing in the project. So in this presentation, I will present the system architecture using two viewpoints. One for the context view, which kind of shows the main external systems and stakeholders that are interacting with the decent system. And then the next view is on functional viewpoint, which kind of decomposes the system into functional components. So like you know, the decent system is targeted for local areas, for neighborhoods and districts, and especially for situations where we have different or multiple energy vectors, like for example district heating and electricity that are used together, for example in heating of the buildings. And then the decent system needs to get a lot of measurement data, of course, through the from the building infrastructure, as well as send different type of control commands to the building automation, home automation systems, as well as other type of local energy systems. Then, of course, important stakeholder is the consumers and prosumers that either live in the buildings or own the buildings. And for them, the decent system provides automated flexibility and energy management. Key part of the project is also local markets and peer-to-peer energy trading, which is automated by the decent. And of course, the decent needs to take the preferences of the consumers and prosumers into account. The focus in the project has been on this local cross-community energy systems, but of course we don't want to create like local optimas and silos, so we need to also enable trading with other parts of the energy systems, and here the aggregator role kind of represent that part of the interaction. And in practice, aggregators can interface with decent through similar trading mechanisms that are provided for the consumers and prosumers. So trading in the local heat and electricity markets to kind of aggregate the local flexibility then to the global level. Okay, maybe Markus, you can go to the next slide. So here we then decompose the system you saw in the previous slide into functional components, and we identified, let's say, 4 different functional components. So starting from the top down, there are the local market infrastructure, both for electricity and heat. Then for every consumer or every consumption site, let's say, we have a trading agent, we have an energy management agent, and an IoT middleware. The trading agent is the part that tries to maximize the value of flexibility for every prosumer and consumer by trading in the local markets. Then we have the energy management agent, which is basically provides the automated flexibility and energy management. And then we have the IoT middleware that provides the interface to the building infrastructure, to the sensors and energy measurements. And there, especially in the project, we work on wireless communications and then security and privacy. And of course, the security and privacy is something that spans across the whole value chain. Okay, but these are the main building blocks, and next you will hear more detailed presentations focusing on these different building blocks. So thanks from the architecture and use case part, and now I think we can move forward.
Yes, I guess now it's my turn. Hello and welcome to the final workshop. My name is Joseph Schindler, and together with my colleague Erkin Kiran, we will talk a little bit about the IoT interfacing with an example of the battery storage. Yes. So first I will give a short introduction about the battery storage. What is the motivation of this minor project that we did inside DEcent project? Then Erkin will explain the communication protocols that are possible, and of those we chose one. And last but not least, I will demonstrate the implementation of the battery storage. Yeah, of course, we have this decent idea with a smart neighborhood where the cross-commodity market helps to use energy efficiently. And of course, we have EVs or electric vehicle chargers, which are the components that are connected to the power grids. The EV charging can happen in private households, which is exclusive, and in business areas where it is available for everyone. So we need to somehow reserve those, and we will have several charging stations. So there can be some problems from this. Maybe the grid capacity is not great enough. How do we organize it, control it, and who takes care of it? And what about the secure communication, especially from a charging station to a remote client or something like that? In Ettersdorf, we have, in general, we have a battery storage, which can be first life or second life battery storage. So second life would be recycled batteries, or yeah. Then we have a charging station to make this use case, and a control system, of course. And we have this limited grid connection. So the battery storage can then also supply energy to the charger if the electric vehicle wants to consume more than the grid can provide. So here's again the decent idea with a trading agent and the local market. So the charging station can interact with this. And of course, as I explained before, we wanted to have a reservation system. So yeah, the charging station is blocked. But which machine-to-machine communication protocol should we use? This will be explained by my dear colleague Yakin Kiran.
Yes, I hope you can hear me. My microphone is working. So yeah, an umbrella term, machine-to-machine communication. These protocols, OPC-UA, MQTT, CoAP, you have seen maybe in the slides here or there, and also you will continue seeing, especially MQTT and OPC-UA in the DECent project. So these are like three the most common machine-to-machine communication protocols. This list can go further, like you can add the XMPP, AMQP, etc. But these three are like the common standards today. First, let's compare them between each other. For example, to give an overview, OPC-UA is pretty much a standard for industrial automation. Yeah, it is widely used in PLCs, in factories, and so on. It's really a standard right now. There is MQTT and CoAP. These are more lightweight options because OPC-UA is pretty heavy and a feature-rich protocol. MQTT is lightweight and it's basically a publish subscribe protocol. Very simple, very easy to use. If you need a publish subscribe, then you go for MQTT. That's why it's also used a lot in IoT, having constrained devices like microprocessors, microcontrollers. There is also CoAP, which is an HTTP alternative, which is a lightweight version of HTTP. It is newer than MQTT and it is somehow less popular than MQTT at the moment. So in the further slides, I will tell you about in each these three protocols, the research we have concluded as part of the DECent project. So with OPC-UA, we have completed two research tasks. The first one is open source OPC-UA security and scalability. So the key result, our aim was, okay, there are some open source OPC-UA implementations, but how about their security and scalability features? Do they overlap, conform the standard, etc.? So the key result is we detected like 4 really popular implementations in various languages, and they conform the standard quite well, and their scalability change drastically, mostly based on their languages. So yeah, you can basically look at the work. It's published in EDFA to look at which scalability is better or worse in which implementation. The second one is feature-based comparison of the open source OPC-UA implementations. There we mostly focused on the features and functionalities that these implementations offer. There is an ongoing research. It is not yet completed. It's yeah, pretty much a lot of progress there, but it's not completed at the moment. OPC-UA pops up over TSN. So the early results show that the different queuing disciplines are more suitable for different requirements and traffic patterns. With MQTT, we achieved to complete one research task, which we call open source MQTT evaluation. There we look at the trade-off between resource consumption and network latency among different implementations. The network latency is mostly caused by randomly randomly drop the packets. That's why you have to retransmit, and then the network latency is changes between the implementations. It is also published in CCNC, I guess in January. Yes, so 3 months ago it was also I presented in the conference. There's one ongoing research. It's also almost done. TLS cipher suite performance on MQTT. So, okay, we want to secure MQTT. We have an options. We can use TLS, but which cipher suite is better here? Because every cipher suite comes with trade-offs. So we look at resource consumption, and which also can be optimized through the choice of cipher suite, as well as adjusting the length and the rate of MQTT messages. Finally, in CoAP, there is one ongoing research. This was also almost at the end, the assessment of security mechanisms for CoAP. So ideally, CoAP is secured with DTLS because it's a UDP protocol. But there is a new RFC 1 year ago published, which proposes OSCORE to make it lightweight security for CoAP. So the early findings show that there are advantages of OSCORE as well as some vulnerabilities, like OSCORE has some privacy issues because some header fields are not encrypted like DTLS. So there is again a trade-off that we hope to present in the research here. That's all. I gave an overview of the concluded research tasks and published as part of the DECent project. Some of them are ongoing, 2 of them are ongoing, the others are completed. And this is the overview of the machine-to-machine communication protocols that I've been mostly busy with so far.
Joseph, you're still muted.
Sorry, yeah, of course, the muting always. Thank you, Erkin, for this short introduction on the communication protocols. And now, as promised, we will have a short demonstration where we implemented OPC UA for the use case of the battery storage with a charging station. As you can see here on the left side, there is a screenshot from the HMI. On the top, you have the limited grid connection as it is to be found in Eltersdorf. Next, we have the battery booster and a charging station. And as we have a simulation here, the electric vehicle plugging and stuff can be done on the HMI. And we also have a simulation so we can speed it a little bit up. Otherwise, the charging processes would take too long to show them here. Next, we have the control panel. It basically has all the functionality a typical charging station has, and it also reflects the charging station that we used from Kiva. And here is some historical and current data on the charging process. As you can see, on the left side, we have the PLC overview. So it reflects the current state of the physical model of the electric vehicle and so on. And it contains also an OPC UA server. On the right side, we have a generic application with an OPC UA client, and it can remotely access data on the OPC UA server and do stuff. For example, we can view the state of charge as in the first demonstration video. On the left side, we have the state of the charge at the PLC, and on the right side, we have the state of charge at the application. And as there is no charging process at the moment happening, the grid charges the charges the battery, and we will see this on both sides. Yeah, next we can do a reservation of the charging station. Again, on the right side, we have the client. So we do the reservation. We choose a time, for example, which is hopefully in the future. Yes. And we choose a date, for example, and then just get the reservation with the RFID, and the server response says the reservation was okay. So on the server side, we will then have the reservation reflected here on the left side, where the reservations are presented, of course. Okay. Next, we start the charging process from the client when there is an electric vehicle plugged to the charger. We can then just start the charging from the application, and we get the feedback from the charger, of course, and the charging happens physically. Yeah, as you can see, of course, time is happening, and the electric vehicle will be charged then. But we have, for example, also this RFID, and if it is not the same as the reservation says, then the charging process cannot be started with the RFID. So we have this reservation functionality here. As you can see, if we change the RFID and we want to charge, then the server says, no, sorry, someone else reserved the charging station at the moment. And if we change the RFID back, the charging once more starts and everything is okay. Yes, that's it from my side so far. Thank you for the attention. I think I will hand over to the next presenter.
Thanks, Joseph. I think it's me again.
Yes. So next is AI for modeling and optimization.
Okay, I guess the screen is now visible. So yeah, so this presentation is about AI-based modeling and optimization for consumer energy and flexibility management. Okay, it doesn't. Okay, now. And so the focus in this presentation is on the energy management agent component. I will first give you a short introduction, then present the main methods and approach applied in the project. We had several case studies. Unfortunately, I have only 20 minutes, so I will just present some details with one of the case studies to give you an overall idea of the work and advances done in the project. And then we also have, as part of the work, made several publications on the AI-based modeling optimization. So if you are interested on the details, I will also present or quickly show the publications we have published as part of the work. Okay, so of course, in the smart neighborhood and in these districts, we can have different type of energy resources. Joseph just showed you the battery and EV charging. The work in this with the energy management agent has mainly focused on buildings, which are also important for energy management and demand response, because buildings are major consumers of energy, and buildings also have a natural storage of energy because they typically have a large thermal mass that can be used to shift heating either provided by electricity or district heating into different time period. And of course, the aim in this work has been to create accurate models on the heating, on the HVAC systems, and kind of enable the flexibility of the buildings to be used both for implicit and explicit demand response at the same time. However, there are challenges. The HVAC systems and heating is quite complex, and there's non-linear dynamics with very long feedback cycles caused by the thermal mass of the building. Also, it's important to avoid, not just to optimize the building with respect to some external prices, because we want to avoid local optima. So it's important at the same time to kind of open the flexibility and offer it for the local market, and through the local markets also for the aggregator, so that it can be used for the situation that is most important, as long as the consumers and prosumers are properly compensated. Okay, this slide shows the overview of the approach we studied in the project. So here is the energy management agent that tries to model and optimize the flexibility and energy of an energy system. And here the focus was mainly on buildings. And the approach we applied was that we used machine learning, mainly artificial neural networks, in combination in some of the case studies in combination with physics-based modeling to create accurate models of the energy system. And these models together form like a digital twin of the energy system of the building that can be then used for model-based optimization and planning in order to find the best way to control the building heating, for example. So this is somewhat, so here we use somewhat similar approaches that have been used in, for example, this game playing AI algorithms by DeepMind, this AlphaGo and AlphaZero. But in order to be able to do that, we first need to create the models that can be used to optimize in the digital world through simulation. Okay, here is the kind of internal architecture. So how is the energy management agent divided into different parts? As already shown earlier, the energy management agent operates between the trading agent that tries to maximize the value in the markets and the IoT middleware that Erkin and Joseph were presenting in the earlier presentation. The energy management agent consists roughly on three types of components. So we have the digital twin, the models here. We have the energy planner, which is like a supervisory controller within a building or within a consumption site. And the energy planner, its job is to optimize the load, for example, the heating load for the site. And this is done, for example, with respect to dynamic electricity prices. It also, and when it has optimized the plan, it informs the trading agent about the load plan it's planning to follow in the next market window. It also evaluates the flexibility, which is basically the deviation, possible deviations from the load plan. And this information is also provided to the trading agent. And when the trading agent is trading in the local markets, it can inform the energy planner about the changes, about the trades via the change to load plan message. And the energy planner uses these models to kind of simulate and optimize or plan the load through simulation, let's say. Then there's also a controller component. There's one controller for each flexible asset in the system. So for example, one for the heating. And once the energy planner makes the plan for the whole site, it also makes the load plan for every controller. And the kind of role of the controller, the job of the controller is to try to track or follow the load plan. And it can also use the models to do model predictive control in similar way as the energy planner is doing. And then finally, the control commands are executed through the IoT middleware. We implemented and studied 4 different sites, 4 different case studies in the context of the energy management agent. We did modeling and optimization for apartment heating. This was done in our test apartment in the Oulu. Then we did electricity and heat demand forecasting for an office building located in southern part of Finland in Espoo, and we investigated new type of neural network architectures here. Then we also had the possibility to work with the supermarket. So we did modeling for the heating dynamics on the supermarket, as well as implemented forecasting models for forecasting the flexibility and electricity loads at TUM's smart office. I don't have now time to go through all these case studies, but just to give you an example, I will focus on the first case study a bit more in detail. So here is a visualization of the case study. So it was implemented in our test apartment, which is roughly 70 square meter apartment. There are quite advanced metering infrastructure. We get the energy measurement from various submeters at 1 minute resolution. There is the heat pump, which was the main flexible asset in this case study. There's also various sensors for temperature, CO2, humidity, and so on that can be accessed by the energy management agent. So the energy management agent is here. It consists of the models and then the optimization and control. For modeling, we used artificial neural networks. I will show more details in the upcoming slides. And then for optimization and control, we studied Monte Carlo tree search, which is also the core algorithm behind this AlphaZero and AlphaGo. Here is a simple illustration on how does the information provided to the trading agent look like. So here are the up flexibilities, down flexibilities. It's now actually in this this time. So this is actual measured energy, and here are some activated down flexibilities and activated up flexibilities. Okay. So basically, the energy management agent consists of modeling, the flexible resources, and then the optimization part. So for the modeling, we implemented two models, two neural networks, one for the modeling the heating, so the energy consumption of the heat pump, and one to model the indoor temperature of the apartment. And for modeling, we use 15-minute resolution. For training and kind of finding the hyperparameters for the models, we used this period, 43 days, and then we evaluated and tested the models in this period, which consisted of 29 days. We use standard root mean square error and its normalized version as error metrics. Here is the temperature model or visualization of the temperature model. We achieved quite nice results, around 3% error in 1 hour, so 4-step forecast. Here you can see the autocorrelation. So how do the errors of the model correlate? And you can see there is basically no correlation. This looks pretty much like a white noise. So it means that there's not much signal left in the errors. So the modeling, at least let's say linear correlation in the errors. So the modeling has done quite good job, and also the accuracy is good. Here is the energy consumption model. It's a bit more complex, so it consists actually on 2 parts. The second part was added just to correct, because there was still quite strong signal left in the error after the first model. So we added that just to try to fix the forecast based on the residual information from past errors. We achieved around 8% error for the energy consumption modeling. Also, this was done for one hour window. Here you can see that there's a bit stronger correlation, but still it's very minor, and it was not, we couldn't find a way to improve the results. So this is also good results. Then these models were used, like I said, in planning and control. So both the energy planner and the controller use these models to plan how the heat pump should be used, but then also to control the heat pump. And the heat pump was controlled by adjusting the set points, temperature set points of the heat pump, and these were the allowed values. I will not go into detail how this Monte Carlo tree search works, but the basic idea is that it kind of form a graph by forecasting different or taking different actions, so the set points at different time periods, and you can imagine that it kind of forms a big graph. And then instead of going through all possible scenarios, which is not possible because for example, if we optimize in 24-hour window, there's quite many different scenarios. So the Monte Carlo tree search is a kind of, in a way, machine learning algorithm, or it learns and tries to search parts of the tree that seem to be more optimal. So it kind of targets the search to those policies, those policies that seem to return better value. Okay. Then how did we evaluate the approach? So we wanted basically to know two things: how much this energy management agent is able to reduce costs when compared to a baseline control strategy. So the baseline was just keeping the temperature at fixed value, and this was done and the optimization was done with respect to Nord Pool spot prices. So here you can see the spot prices for the evaluation period. Here is the price in euros per megawatt hour, and here is the outdoor temperatures in Oulu or in the site during the evaluation period. Then, like I mentioned earlier, we also didn't want to just focus on local optimization, but also wanted to offer the flexibility for the local market and through the local market also to the aggregators. So in this context, it's important that the energy management agent or the behavior of the building is predictable. So the load plans need to be accurate. The response of the energy management agent when it's controlled needs to be accurate. So this was another thing we wanted to evaluate. The evaluation period was 16 weeks between this period, and it was done by simulating with the models I showed earlier, but then sampling errors from the empirical error distribution I showed earlier, not to give the optimization kind of unfair benefit. Okay. So in the first scenario, we just did the spot price optimization. On the top part of the figure, you can see the daily energy costs here, and here the cumulative energy costs compared with on blue is the fixed set point controller, so the one that keeps the temperature at fixed value, and then the energy management agent that was allowed to increase the temperature or drop it half a degree below the 23 Celsius degree. In this evaluation, we only measured the spot price, the energy costs. So this didn't include any taxes or network fee, which typically constitute like a 2/3 of the price. But anyway, the energy management agent was able to achieve a bit below 15% lower costs when compared to the fixed set point controller. Here on the bottom part of the slide, you can see a couple of examples. So the orange line is the energy price, and the blue line is the energy consumption of the heat pump, and this data is in 50-minute resolution. So you can see that the heat pump kind of exploited or learned to exploit the low price periods. It also used quite short bursts of heating to keep the temperature just above the minimum value. Okay, here is another scenario. Here the energy management agent, like I said, is all the time offering the flexibility for the trading agent. And here we want to evaluate how accurate those load plans are and how predictable, how well we have done the modeling, and how well we can, with the controller kind of even improve the accuracy of the models, because we can try to kind of, in a way, fulfill the prediction. So what you can see here is that on blue, you have, this is 1 hour resolution, so that's why the data looks a bit different to the previous slide. It's more low resolution data. On the blue, you can see the original load plan that was done for the day. Then we, for every day during the evaluation period, we selected the hour with the lowest price as lowest price, and then execute the flexibility or demand response event there. The idea was that all the sites would be kind of exploiting the spot prices, and then there would be like a local bottleneck in the network. And here you can see the flexibility that was kind of estimated, so between the blue and red one, and then the green one is the actual measured load. So you can see that typically there's some errors, but typically it's able to quite accurately follow the estimates. And outside of the flexibility events or demand response events, the errors were roughly 5%, and then during the events it was a bit above 7%. So still very accurate results. So just to summarize, we were able to reduce the costs, while at the same time offer the flexibility for the local markets, and this was kind of the goal, to be able to provide both implicit and explicit demand response at the same time. And if you are interested, here are some of the publications we have done on this. Is on this case study, and then we have some others for the other case studies. But thanks, this was my presentation, and I think now we move to the was it trading agent, or which one was?
Yes,
next?
indeed. Yes, indeed. So I will pull up my presentation as well.
If the presenters want to open the camera, of course, you are invited to do so.
Very good. Good afternoon, everyone. I'm Jan Segerstam. I'm the strategy director of a company called Enerim. We used to be called Empower IM, but since June last year, we've been acquired by capital investors Klar Investment Partners, and are now working together on international growth on issues not so far from what we've been developing here as well. So what I'll do is I'll be presenting shortly some of the results that we've been discovering in the Descent project, and also I will talk a bit about the background. So we've studied what it means to have a cross-commodity energy market environment. When we look at the optimization of heat and the optimization of electricity, it's one thing to look at the optimization from a technical point of view, and then like we just heard on the electricity part, we can take a look at the market part as well, with the implicit and explicit demand response scenarios that were just presented. Now, when we look at the energy market as a whole, it is comprised of a very structured environment. It used to be that you would have suppliers and DSOs and messaging between them for consumption on metering points, and the underlying market would operate only on the wholesale level with TSO connected resources on and large production. Now, this is no longer the case, so we're seeing a much more complex environment where the data exchanges are forming around either national information exchange structures or national data hubs, whichever. From a business standpoint, it's actually the same thing. From a technical standpoint, there are multiple differences. So in that kind of environment, when we look at the emergence of local resources and local flexibilities, they will have multiple ways of generating value. So there's the local value, and then there's the wholesale and public retail value of both the load and the generation at metering points in the energy network. So when you optimize between the heat part, which right now does not constitute a market in itself, but could be a local market, which is something that also was discussed here in the Descent project. Then we have the electricity part, where you can also have a local market, but you also have the wholesale market. So what we were looking at and what we were working with was to work with the valuation and allocation that benefits the entire energy system, i.e. looking at giving the information for the local market on what is the opportunity on the overarching market, and also then receiving the information from the local level on what is the situation, what could be done, what is the available flexibility, how could that be used, so that the value equation for looking at the local value and the wholesale value and the value between commodities, that is heat and electricity, that actually can be calculated upon. So in this rather complex environment, we are the link between the energy management and the market, if you will. And then we of course also have the local smart contracting working on a peer-to-peer basis, which was done by the partners here in the project. So we were also collaborating on interfacing with that. So if you look at the value, you need to look at both the wholesale and local value together in order to see what is the actual value of the commodity. When you look at that, we also discovered that when you look beyond what we've been doing in the Descent project, there's a point in looking at how we could link the bids between the different commodity markets and have structures that would be interoperable between the different commodity markets, so as to basically allow a heat market to form where you also allow an energy, or let's say electricity market to be exact, to form. If those bids could be linked and the let's say market mechanisms would work in unison, then there would be even better opportunities to achieve liquidity, which is also an issue when we look at price formation in markets. So when you then have all of these markets and the different opportunities, you, after the transactions, end up looking at, well, how do you settle all this? And that's where we're coming in, so that we can enable these kinds of local entities or local marketplaces or local communities to do their thing and then be part of the overarching mechanism, so that when the local entities interact between each other and also affect the balance position of the balance responsible parties who are providing the balance energy towards that community, that can be taken into account. There's obviously multiple ways of dealing with this, and different energy providers have different kinds of products to enable this on the retail level. But it's also possible to just directly connect to the wholesale world by becoming a party yourself, and that's something that we can also enable. So that's why we're interested not only in the trading part, but also the settlement part of the transactions, where the value is traded between the different participants. So if you then look at the local scope and the peer-to-peer trading, smart contracting will allow this to work in an efficient way, and I believe we're going to hear more about that from the other partners today. Here, what's important is that we have the right data there so that we can come up with the value when we go up in the value chain to the wholesale part as well. So that's why we've interacted, so that we understand what is actually part of the information exchange. And that brings me to the integration and value distribution with market data exchange. Sorry for the Finnish details in the picture. The picture is basically about the different data exchanges between the different entities when we look at day ahead and intraday market interchange. And this interchange is important so that we can provide the value on multiple levels. So if you participate in the day ahead, then once you get the information on what is the value on the day ahead and what is the situation on the day ahead, you can then make your decisions for the intraday. Like we heard in the previous presentation, you can basically work with getting price information and then adjusting your loads or generation accordingly, and that's all well. But in some cases, depending on whether you do it with the knowledge of your service provider or not, you might induce a situation where there is a discrepancy in the intraday. So imagine, if you will, a case where there's a very high day ahead price peak, and everybody says, yes, oh, this is a good signal, I will now turn off everything. And everybody actually turns off everything, meaning that then we end up with a spike in the other direction, because it's not really about a set level. It's about being where you're predicted to be, and if you're not, the electricity system, that is not in balance, and therefore you have to have balancing actions which are then paid on top and incur costs done. So that means that having activity and having capability on working on multiple levels of different markets and taking into account the different value opportunities is important for the grand scheme of things. If only a small handful of people act and just optimize against one price signal, that's not a problem. That's fine. There's no problem with that, because it kind of goes out in the statistics. But when you start to instigate it on a more systemic level, then you need to take into account how the system actually works in the background for the pricing and the reasoning for the signaling, in order to keep the actual energy system stable. So we see that there's much to do in the future as well. I mean, we got important insights in this project on how we could work in the cross-commodity environment and link that to the market environment in a good way. But we feel that working on true linked markets for the physical electricity and heat would provide very interesting topics for future European research, specifically in the countries where we have established heat networks, because they can operate generally as a large energy storage that can be taken into use as a flexible resource when we see the electrical renewables as exhibit a lot of volatility. So there's a lot of value there to unleash. Also, we need to look at the different value drivers. So how do we identify the kinds of value drivers that together provide the optimum value for different situations, which let's say in a region with constrained TSO connections could be very different from a region where there are constraints in DSO level connections, which is again very different from an area where you have a good network access, but you have less access to generation resources that are controllable, and so on and so on. So looking at the cross-commodity space and in that light would provide even more opportunities to generate value in the transition that we're working on, all of us, in transforming the energy system, and there's still lots to do. But I think the Descent project has been a very good delving into how to work with a market-oriented heat electricity approach, and it's been a very interesting journey for us with all the partners. But that's basically it from me, and I will stick around for any questions, but then towards the end, in about an hour, I will need to hop into another meeting as well. But feel free also to send me any questions either in the chat or just ask. Thank you very much.
Thank you very much, Jan. The next one is market clearing and mechanisms, and will be presented by Fortiss and Framatome.
I think we have some confusion, but Joseph, then you show the first slides.
I will probably show all slides, Marcus. Okay.
Okay.
Because then we don't need to change.
It makes sense. Sorry, I stole your sharing, so you need to reshare.
Oh. I did miss that. Okay. Yeah, now hopefully it works. And thanks, Jan Stegersman, for this perfect introduction, because you already talked about the cross-commodity markets and...
No, Jan Stegersman, terve.
Sorry?
Mä olin tuossa kiinni pitämässä yhtä esityksestä yhdessä kokouksessa, niin päässyt puhelimeen, mutta ajattelin, että mä soitan saman tien takaisin.
Okay, for non-Finnish people, this is difficult to understand. But I think it's not addressed to us.
Maybe you should mute. Jan?
Joo, siis se pösö, se 1007, kyllä.
Okay. Hopefully Jan will recognize that he is still unmuted. Okay, again, thanks for the introduction. For the perfect introduction.
Selvä. Ei tähän niille jarruneille nytten mitään, niin, niin tietää ton, niin, niin täytyy sitten vaihtaa jossain vaiheessa ne sylinterit.
Someone with the rights who can mute him.
Niin, ei siinä mitään. Niin, satulat edestä ja sitten sylinterit takaa, joo. Joo, kyllä. Niin, niin.
I think Marcus or Satu should.
Okei, no sitten se vaan se jostain saattaa se, mä mietin, että olisiko siinä niin lohkolämmittimen niin jossain, mutta hyvä, ettei ole mitään moottorin.
Force muting.
Sorry.
Niin, se on ihan jees.
So you see, do you have the rights to mute?
Can you just mute him? He is talking about the car repairment and the brakes of the processor.
Niin pääseen siihen aikaan.
You can mute him. It's not relevant to this.
Hyvä. Niin, mitäs sä meinaat, minkäs kokoinen paketti tuli?
Satu or Marcus, could you mute? I don't have the rights.
Good.
Yeah, okay, now it's...
maybe it's over.
Okay, yeah, anyway, we will talk about the market clearing and mechanisms. Yeah, let's dig into it. First, Marcus will talk about the implementation in the Dissemination, which
Mä tuossa just ennen
Maybe you see call Satu or Markus so that they can mute you.
Hyvä, kiitoksia. Joo, moro.
Jan. Jan.
Jan?
No.
You're still unmuted.
I also wrote him a chat message, but he probably doesn't. So I
Okay.
think
Sorry. Now it's
perfect. Good. Yeah,
Thank
please
you.
mute yourself, Jan.
I will mute myself. I'm very sorry. There was a telephone call.
No problem. Thanks.
Okay. Yeah, thanks again for the perfect introduction. As you talked about the cross-commodity markets, Marcus and me will now introduce how we implemented those in the DEcent project. First, we will talk about the DEcent standard, which is the local energy market based on merit order. Then I did something to address these linked markets using the gossip algorithm, and later on I will give a short comparison between both approaches. Yes, now it's time for Marcus to introduce the blockchain market.
Right, so we heard a lot about blockchain markets. We used the IBM Hyperledger Fabric. Of course, during this project, we also experimented with the Ethereum-based Energy Web Foundation, which is quite popular in the domain. But we chose for that Hyperledger Fabric framework, so we built up a permissioned blockchain, which we implemented, and we had a Hyperledger Explorer instance running, which we put on our public port, which was available and used to check the current state of the blockchain so that every partner is aware that the system is up and running. Of course, it lacked of stability in the first iterations, but we tried our best to get a stable version up and running. Of course, we also implemented a client application in order that every partner and every partner side could interact with the blockchain and the smart contract in order to post offers and also post demands, whether they want to sell electricity or heat or purchase electricity and heat. And due to the permissioned approach we chose, it was also represented by an authorized peer, and we also provided the client application in order to interact with the blockchain. And of course, not only the clients participated at the market, but also the operator. I think that was also visible in Jan's presentation. I'll have a closer look on that on the next slide, but the market operator was responsible to clear the market and had a dedicated or a specialized role according to the certificate. So if we switch to the next slide, we see the overview of the whole market. So we had a certificate authority in order to authorize dedicated peers or newly peers which appear in the market, that they can execute the commands on the smart contract. Of course, we also had an endorsement policy for every peer in order to promote the offers and demands which were placed on the blockchain, so to say. And so we see within that box, we have the different entities, the different houses and prosumers in our system. Everyone had two peers in order to interact with the market and also to do the validation, so building the consensus mechanism. And of course, what we see below the box, we have that market or operator instance, which could also interact with the blockchain in order to do the market clearing. So the offer interface of the smart contract had certain information which was included. So the amount of electricity, how much I want to offer on the market, what is the price I'm willing to sell that amount, also validity period. From and until or the time horizon within which the offer is valid, and also can be provided to another entity who has matching demand. And if we go to the next slide, we see the controller, which is also included in every peer. It operates more or less the offers, and only some operations are, as explained earlier, are available or accessible for dedicated roles based on the certificate that peer brings with it. So every entity was able to create offers, to delete offers, to update offers, of course, only from their own peer, which they set. So you can't delete any other offers from other peers or participants. But of course, you are able to query offers and also to query for organizations which are participating at the market. And only the operator role, according to his certificate, was also able to do the market clearing. And that clearing mechanism was implemented using a merit order principle. So this is quite common in the day-ahead energy markets. And here on the right-handed side, we see more or less how the merit order principle works. So we have two ordered lists, and also the ordering was done on the chain, so within the smart contract. So it was an operation. And then we have the supply. Everyone who provides electricity or heat in an ordered list by a price ascending, and the demand the other way around, so with a descending price. And the merit order price is where those two graphs intersect. Of course, we also had several special cases which we evaluated within a paper together with Joseph or Framatome or Correlation. And also these are implemented correctly, at least according to what we did in the paper. And those two markets we implement, so heat and electricity market, were up and running. The merit order mechanism and the matching operation also allowed for partial matchings. So if only a subset of, or a part of the quantity of the energy offered or requested could be satisfied, this had happened. And we also allowed for linked offers. So for special cases, when I have a heat pump in one house, I can only offer heat if I upfront could purchase electricity from the other market. So also this logic was implemented using the smart contract. We go to the next slide. Here is more or less again that principle of the different organizations. So the clients running at the different partner sites with the two peers within the client, which were able to really post offers or post the demand or delete it or update it. It was shared and distributed by all the authorized parties within the virtual neighborhood network, so to say, and placed on the blockchain, whereas the operator was responsible in the end to do the market clearing. And based on that market clearing, we also got the approval, more or less, for dedicated orders, which matched with offers or demands from the other clients. And on the last slide, I think from my deck, no, we also did the market evaluation, of course. Therefore, we used our own simulation environment, which was capable, or we implemented 100 simple buildings, which did 10 bits every 15 minutes for each building. and we investigated different consensus mechanisms. So in order to agree if an order is approved or not, or if an offer is valid or not, and if the matching could occur. So proof of work is what mostly everyone know in terms of Bitcoin, so the currency. So every participant is given a very complex task, and the own hardware is used to solve that difficult task in order to validate a block on the chain. And another approach or another consensus mechanism is the proof of stake, where the next participant who is allowed to validate a block on the chain is determined by the means of a weighted random selection, whereas also this is not a fair approach, because those participants who are earlier in that network are weighted a bit more, and therefore the selection is not as random as proposed. And there is also a third consensus mechanism we looked into, the Byzantine fault tolerance, whereas all the registered identities, so all the participants with an available certificate or with a valid certificate, were chosen, as well as a redundant reconciliation for the validation. And in the table on top, we see for the different options, or not really options, but the different aspects we had a look during our investigation. So node identity management, of course, proof of work, as Bitcoin is an open system, as well as proof of state. Whereas the Byzantine fault tolerance system is a permissioned blockchain, so to say. So you need to be validated by all the nodes or by the certificate authority, as we used in our Hyperledger approach. Then we, of course, had a look at the energy saving potential, because what we hear often in the public, using blockchain is a waste of resources and a waste of energy. And at least for proof of work and for proof of work, there is no energy saving potential, because you need to use your own hardware to solve these complex tasks. Whereas for the proof of stake, of course, there's a partial potential to save electricity. And within the permissioned approach, as for the Byzantine fault tolerant consensus mechanism, we see the most energy saving potential. And of course, also due to security reasons, we looked at the tolerated power of adversary. And so computing power, so if you have a sufficient amount of computing power for proof of work, then you can more or less manipulate the blockchain. For proof of stake, it's a bit more difficult to do so. And in the Byzantine fault tolerant system, a number of 33% faulty replicas is required in order to manipulate the system. When it comes to the computation time, so the complexity, in order to do the market clearing itself, mostly we had the complexity of n log n in order to sort our lists of offers and demands. So also the clearing time increased line arithmetically to the number of bits which were available in the network. So these were our evaluations in short. And on the next slide, now this is my last slide, we see a short video that we really also did some implementation in order to start up the market using Gradle. And here we just see if we run the video. I'm not sure if it works properly. Yeah, so this looks good. So we have those two market clearing services. So the operator role, we have initially those 5 organizations which participated in the project and also did the clearing periods for 15 and 30 minutes ahead in time in order to compensate for the longer time until heat is really available. So therefore also the time horizon where the clearing happen is also a bit higher than the usual day ahead market time periods. And what we also saw is the posting of offers, which was tracked and monitored by the market controller. And then I would hand over back to Joseph in order to continue with a gossip approach we also had a look into, or not we, but
Yes.
within the project.
Yeah, exactly. Thanks, Markus, for the presentation. As Markus already said, I also looked into an alternative market or alternative algorithm, which is the gossip approach, and I also wrote some papers about this. In general, for the gossip algorithm, you need a communication network, and the idea is that an information is spread all over the network by peer-to-peer information spreading. So as you can see, we have a random gossip approach where one knowing node addresses a randomly chosen neighbor. Then we have a geography network where the hop limit is not limited to 1, but a node can always access any other node within the network. And we have the broadcast approach where information spread is done to all surrounding neighbors. For the peer-to-peer consensus, we did not exactly use the information spreading just, but it is a more bilateral or a bidirectional communication. So the local consensus is done as shown here. We request another server, and then in the main calculation happens during steps 8 to 10, where the cost minimum is calculated. So the cost minimum or optimum of the cost functions needs to be found within 2 participants. And to get a better idea, I plotted here some cost functions. For example, a photovoltaic power plant, it does not care how much it puts out, and thus the cost function is just a flat line. Next, we have a battery storage with who can also have negative power outputs. And last but not least, we have a fuel-based generator, which can be represented by maybe a more complex cost function. For example, at low power outputs here, we have bad efficiency, and thus the gradients are higher. And for example, in the low and the high regimes, we have high gradients due to high wearing on the components. And the global consensus compared to the local consensus is the minimum overall cost with a steady overall power output. So within all entities or participants, the power output is given at the beginning of this consensus finding, and then with this peer-to-peer trading or local consensuses, over and over again, we reach then a global consensus by minimizing the cost between 2 peers. So this is the goal that we want to optimize. We implemented, for one paper, we implemented 2 approaches. In general, the OPC-UA solution was reliable and did a good work. Next, I wanted to look into the results from this simulation. As you can see, we have several fixed nodes who are defined, for example, by polynomial coefficients. So these are the cost functions and initial values, for example, and boundaries, so the minimum and maximum power output. We varied the number of participants, and they always, if we ran a scenario with 8 entities, we chose the first 8 entities, so it was comparable. Next, we also differed some other parameters in the scenario. For example, the delay. A server waits for a time duration where it is accessible for other nodes to be addressed in for the peer-to-peer consensus. Otherwise, if there was no time delay and everybody would just try to reach out for other nodes, then there would be that it would get too crowded and the communication would break. We ran all the simulations for 90 seconds and we did each scenario 3 times. And here we can see the result for one run. As you can see, we have this all the small lines represent the costs that each entity has, or how they develop with after all the tradings. And the red curve shows that the overall, the sum of the costs decreases, which is the optimization goal, of course. Yes. We have a fast drop in the beginning and an intermediate drop afterwards. But in general, we wanted to have a comparable behavior with the merit order, and this is what I'm showing right now. The merit order has, we have this gossip approach that I explained before, and to compare it, we need to look into the merit order, how it works, and then we defined that it is comparable. So first we have the bits which are represented by energy and price for one market clearing interval, and we have the sorted queues. So the demand and supply queues that Markus already explained. Then there is a matching price, and of course, the optimization goal is to maximize this integral that I highlighted gray. So the total cost drop should be maximized by the merit order algorithm. And this leads to the comparability. We showed that the integral of the bits is exactly the cost function for the gossip. So we approximated some bits from a merit order scenario and saw that the deviations were about 0.5% at maximum. And as you can see, the highest deviations are where the bits are changing. So from 0 to 200 megawatt hours, we have the first bit. Afterwards, we have a new price, and then again a new price. And at these definition edges, we have the highest deviations or errors. So the conclusion, we have the same optimization goal because we can translate one function to the other. So the bits are translatable to the merit to the gossip cost functions. Difference between both approaches is that the merit order needs a central calculation unit, and the gossip approach is a real decentralized approach where we have a real peer-to-peer trading. The merit order market is more efficient because there is this coordination, and we have a fixed algorithm that can be run on one entity, whereas in Gossip we also need the communication always. But the Gossip, for example, has a better resilience. For example, if in merit order market, the market entities breaks, nothing works. But if we look into Gossip, if one client breaks, there is no harm on the overall system because all the others still can trade. One other thing that we can do in Gossip markets is we can have more complex cost functions. I would just go through this. There is a problem that in merit order we the gradients can only increase. There is no possibility to decrease a gradient over the energy output because the bits will be ordered by the algorithm. So Gossip solves this one problem, and then another issue is conditional bidding. If we have two markets that are cleared at the same time in merit order, the conditional bidding is very difficult, and there is, from what I know, no solution that does this just fine. But in Gossip algorithm, there is, because we have these micro trades between always between two participants. You can define boundaries for your cost functions. That are conditioned to the cost function or to the current set points. So for example, here we have in the end we have it's difficult to say. I'm very restricted with the time, so I cannot explain this more properly. But as an output, we have that the power outputs were set closer to each other because the deviation is limited from the conditions. Otherwise, this output for heat could have grown to a higher level in merit order. So here the Gossip approach also has a small benefit over the merit order market. Yes, I worked on that, but this is not part of this presentation now. And thank you very much for your attention. Let's hand over to the next presenter.
Yes. And the next part is the security enablers by Wirepas and TUM. So Lars.
Yes, so I will just take it away and hope you can see my screen.
Yes.
Great. So, all right. So now we have talked a lot about the functionality, but a small aspect DEcent was also looking at the security of all of this. And if we, okay, now it works. So if we look at the architecture of DEcent, it's rather simple. We have a market somewhere, and then we have participants who trade heat or energy or anything, and they need to collaborate somehow, and the market then comes up with the price. However, as we have seen in the recent 1.5 hours or so, it's a little more complex. So yes, we still have the market. Depending on how we choose to implement it, it might be a central place where all offers are collected. It might be decentralized. Then we have trading agents by each of the entities. Behind that, they actually have a local energy management agent, for example, which actually predicts how much energy is needed or how much energy can be sold. And on the local side, actually, it's getting even more complex because every participant has its own unique setup with heterogeneous devices. There are different heaters, stuff that consumes energy. They might have local capabilities to create energy or none at all and are purely relying on suppliers. So yeah, that's overall quite complex scenario with many different aspects. However, it's actually possible to divide this architecture into two more, well, homogeneous parts. And there, on one hand, we have the market domain, which includes the market itself and the trading agent. So it's basically where all the trading happens and where the partners interact with each other. And then on a more local side, we have a participant domain with all these unique setups, which is quite heterogeneous, as I mentioned before there. And even though here it's marked as a single participant domain, which includes all the partners, you can imagine that, of course, each participant has its own domain, which is isolated from the others. So you have these isolated participant domains that are local for each partner or building site, depending how they participate in the market. And for example, for VTT, it's quite irrelevant how the setup behind the trading agent looks like at TUM. And yeah, so therefore, we kind of derived that the market domain is quite homogeneous and it's shared. It has to have its own security mechanisms that are required to secure that domain, and the same goes with the participant domain, which has different properties and characteristics. So for the market domain, I mean, there are plenty of motives to disrupt it or tamper with the market. First of all, if you are an adversary, you might want to have monetary gain. So you might want to sell your energy at a high price or your heat and buy it at a very low, as low as possible. So you kind of have the economic incentives to actually tamper with it. Then even if you don't care about your own gain, you might be a bad person and try to have somebody else lose money or, destroy some stuff. And, or if you are just into, destroying things, you might want to disrupt the whole market and disrupt its operation. We heard earlier a little about resilience. That's quite good in the gossiping approach. And yeah. Then finally, there's also confidentiality, which you want to break. There are some privacy issues. For example, if there are some private households that are part of the market and you're monitoring the orders of supply and demand, you might be actually able to infer information. So for example, if TUM is participating and consuming quite a lot of energy, during the weekdays, and they do not consume energy during the weekends, you can actually say, well, probably everyone is on in the weekend. But if you have private households, you can also deduct other sorts of things, like, for example, if they are on holidays or somewhere gone there. So you can actually derive information about private matters there as well. So in order to secure this, we need quite a lot of mechanisms or different stuff that we need to have figured out. So first of all, the market domain itself, the messages that are being exchanged need to somehow be structured and standardized such that you can sanitize and validate the stuff that is sent around. We mentioned earlier there are 6 message types, and yes, they have to have some structured format with the message types and the data types that are sent around and the information there. Because if you are tampering with it, you might be able to break some implementation there and take over other devices and break all sorts of stuff. Then, of course, you need to secure the messages or information, the transport itself. So you have to have integrity such that nobody can tamper with messages. So, for example, altering offers or imposing somebody else. So there we need to have some authenticity, which is in our demonstrator provided by the certification authority of the blockchain market, which is quite nice there. So we have that. And we also need, of course, standards to secure the message transport. So the our demonstrator supports HTTP and MQTT data exchange. So HTTP by default is not secure, so we have to rely on underlying TLS connections to make it secure, but we have to actually enforce these standards, and the same goes with MQTT, which is not encrypted or authenticated by default, but there are extensions to secure it, to give means for confidentiality and authenticity and, well, also integrity. Yeah. So that's for the market domain. And, well, no, yeah, sorry. Last one, I forgot. All of these mechanisms that we need and require should be distributed because, well, yes, in the simplified architecture, we have something centralized, but in general, we're dealing with a distributed system, and therefore, we need mechanisms that support this. This is especially important for the public key infrastructure that is required to run something like this. Then, if we dive into one of the participant domains, for example, here on the left-hand side of TUM, of the general architecture, TUM is represented by a trading agent, which does place the offers and does the trading with other participants, and is highly interconnected with the energy management agent because, well, that's where we get the sub-demand and the information if we can actually sell, if we have too much energy or heat that we can sell again to the different partners. And that energy management agent is highly interconnected itself, then again, to devices on the local side. So here we have, well, smart meters, heaters, if you have a smart home and, or, well, the smart office at TUM, where you can build profiles of people who are, or not of people, but of how offices are being used and how, well, the local energy supply is actually going on. And this also, of course, needs to be, is highly unique for each setup. So this might be the place for TUM, but for VTT, for supermarket, things look quite differently. Again, the devices are vastly different depending on their purpose. And, well, IoT devices are often low powers, low powered, which means they have low computing powers. And they're limited for cryptographic possibilities. Sometimes they're even battery powered. So, well, lifespan is a goal. So you are limited there as well. And if you go shopping and try to buy a thermostat, there are already 10 different vendors there that you can choose for. And most of these vendors are not interoperable. So this is something that, of course, can be solved or has to be solved. And to secure the whole thing, and I guess we at TUM have the VSL there, which actually enables all of this and provides some of the mechanisms that I will get to later on. And then the network structure is also quite differently. Some devices are connected wired, others, for example, probably the battery-powered ones are connected wireless via Wi-Fi, now maybe with a 5G narrowband or LoRa, depending on the use case. And yeah, so participant domain is a lot more different than the market domain. And here we have, of course, also attacks that are unique to there. So an attacker might want to falsify the decisions of the energy management agent. Therefore, he wants to manipulate the data that comes from the devices, maybe simply drops it or insert other stuff to, well, influence the EMI, and then finally also influence the trading agent. Maybe also simply wants to remote control a device. So for example, if you have a lock, smart lock, you do not want some adversary to take control over your door, or if you break something or introduce new devices, then actually can also supply data to the EMA, which also influences the trading. Or you can also simply denial of service devices and take out well, some participant domain. And therefore, we need some mechanisms. And here, in contrary to the market domain, which is usually quite limited in participants as we're in a local neighborhood, there are plenty of devices, or it is possible to have plenty of devices in such a participant domain. And therefore, we need to have some scalable bootstrapping mechanisms. I think Wirepas looked at these, how to securely get devices into the network and bootstrap into the participant domain such that you are aware which devices there are. Yes, we have the limited possibilities for cryptographic protocols, but we still need some authentication for the devices. And since we are so limited, most of the mechanisms go for symmetric cryptography, and therefore we need to have some key management mechanisms. So we did some research and publication on the rekeying on such constrained devices. And also what's very important here, that you are actually, so there's this cyber component and the physical component, that you need to be able to verify the state of a device, such meaning that you can actually trust that if a device says that it has executed an action, that you are sure that this actually has happened and it hasn't only occurred on the cyber layer and the device has done something different. This usually falls under the term of trusted sensing or trusted acting. And so we also do some work there on trusted acting, where we can actually verify the execution of device commands or actions via a side channel. So to actually detect if all of that happened. And yeah, so here short overview on that with the cyber physical part. So we want to actually verify that the stuff has occurred with a side channel. There are different side channels that you can choose from. You can, well, use the power consumptions. If you have a meter connected to the device itself, you can use the power trace, or other side channels, audio or light emission might be something. And then you want to correlate this with actually the commands that were sent to you with the network. We built something that's based on Modbus, which is an industrial network for industrial devices, and use audio as a side channel. And actually, we can, or it's probably possible to use this combination of the information of the side channel and the network messages to actually determine abrasion of devices. So if something breaks, determine if the behavior was as intended, or on the other hand, if we find that a device performs something a little off and odd. And yeah, but this can also be used to verify that actually an action has occurred instead of just you going for, well, anomaly detection. Yeah, so this is a short overview on the security perspective for that. And I guess we're 5 minutes, then we can head over to the next one, which is the demo.
Very good, yes. And yes, so next thing is, so it's very good that we've seen now lots of interesting building blocks and also done a deep dive. I really enjoyed that, and everything together is a part of the demo, and it's shown now. So I hand over to Joseph for that.
You are again muted, so one more time.
Sorry.
Good
Thanks,
job.
Lars. Yeah. Oh man. Yeah, thanks again. And now this presentation is the last of mine. Together with Marcus and Lars, I will present something about the co-simulation. Yes. Here's a short summary. So first we will present the decent virtual neighborhood as a motivation again for this topic. Then I will talk about some mechanisms used for the scenario, which is then stated in section 5. Afterwards, I will present 2 demonstrations, or 1 demonstration and 1 result demonstration, and give some main results from the simulation, from the market simulation. Yeah, so first, Marcus, please go ahead.
Thanks, Joseph. So this is the figure we have seen recently during the slides. So this is our envisioned virtual neighborhood and how those buildings intercooperate within the district and exchanging loads, flexibilities. Also, we have those smart houses. And on the next slides, we show what we have really implemented. So we have that heat and electricity blockchain-based market. We have the Framatome virtual participants, which are introduced. Also the battery storage for a district, for a quarter. We have the VTT apartment, which was introduced by Jussi Kiliander, and how it operates. And also we have the VTT supermarket, for which we also have real data, and also the TUM apartment or the TUM office building, the floors, which was equipped with sensors and smart meters in order to provide real data. And also at Fortiss, we had the heat and cold storage demonstrator, and all those real entities and also the virtual participants were connected to our markets for flexibility sharing. And on the next slide, we'll hand over to Joseph in order to go deeply through the evaluation of our virtual neighborhood.
Yes. Again, we have this decent idea, decentralized cross-commodity market. Of course, we used the merit order mark approach or algorithm that was explained previously, and Fortiss provided an API with several functions. Here are the most important ones. We need to post the offers so the auction knows that we are offering energy or that we're demanding energy, and we need to get the clearing after the market algorithm determined which offers have been matched with each other. Next, we will talk about some mechanisms. The first one is the outside trader. So, of course, on the market, we have we can place bids, which are demands and supplies. Here, as shown as red and blue curve. Some of them may be flexible bids, where you can make money or optimize the power system, and others are fixed needs. And by placing those on the market, you can minimize the cost with game theoretical thinking and strategies. But these fixed needs, if they are unmatched, as you can see on the right side, they need to be compensated. For example, a house can, if you need 2 kWh and you place the bid for those 2 kWh, you cannot say afterwards, okay, 1 kWh is enough, because the people inside still want to watch TV or something like that. So in our scenario, we implemented we added the outside trader, and this outside trader is always buying at low prices and selling at high prices. So from these prices for heat and electricity, we have somehow the boundaries. It does not make sense to place a demand bid higher than 30 cents per kilowatt hours, for example. The outside trader is handled outside the market loop, so every organization has to think about this compensation mechanism on its own. And for example, the electricity would be in real life the contract with your retailer, and the heat outside trader is more like an own production. So if you really need the seed, you would then produce it on your own, but for a rather high cost, for example, here 15 cents per kilowatt hours. Next, we need to, for this 15 minutes market, we need a scheduler who loops always in these 15 minutes and takes care for timing. Of course, within these 15 minutes, the entities and market agents need to be triggered for processing. The scheduler, because it contains several market agents, gets the market clearing and incorporates the clearings at the market agents. It also triggers the forecasting of the physical models inside the market agents and the logging. Next, I want to shortly give an overview of the market agent itself. It equals an organization and, for example, contains entities. The entities are then the real physical models or things like a battery storage, a house, a PV plant, whatever. And the market agent also takes care of the offers, so there's a stack for them. The market agent distributes the scheduler's triggers to the entities, for example, the processing and the forecasting, of course. The forecasting then produces new offers for the future time slots. And another thing that the market agent does, it interprets the matches clearings that are provided by the scheduler with several information from the offer ID and organization name. It then distributes the transferred energy to the various entities. So the models know that, or the entities know which is the set point for the very time slots. The entity, as I said, is the physical model, and therefore it contains maybe several commodities like electricity, heat, but also, for example, hydrogen is a possible commodity. And all the commodities are represented by polynomials and edges, which define the set points that are possible. And of course, the commodities track down the imbalances that have been done due to trading and stuff like that. The entity also incorporates some basic functionality as logging. And it is the parent class for the physical models. As explained, we have the heat and cold storage for Fortiss, or the battery storage, or some virtual models that I need to explain a little bit more. for example, the house has a fixed, or the houses that we use as virtual entities have a fixed baseline with peaks, for example, during morning hours, evening hours, and rather low or average demands in the meantime. As explained before, houses need to compensate all the unmatched bits because they are not flexible or they have fixed demands for heat, for electricity. And the forecasting would then look like this. The outcome is the bits for the commodity. And as an input value, we have the consumption baseline, which is then calculated somehow to a price, and of course the amount of energy. Next, we have a heat model for the houses, which comprises capacity and isolation model. The isolation model contains the indoor versus outdoor temperature, and of course this leads to a heat demand. And the capacity model is driven by a desired indoor temperature preference baseline. And if it changes, of course, the house needs to be heated up afterwards and cooled down. And as you can see, then this gives a baseline that looks like this. It is derived, or the scale is derived from the annual heat consumption and the degree days, for example. So we get the scale. It's about, in this example, about 2 kilo or 1.5 kilowatt hours at max for one market interval, which is then 6 kilowatt of power. The forecasting is more flexible than the electricity because we can use the heat capacity of the house. So not all unmatched bits are compensated from the own heat production, but there is more like a P element that compensates the baseline deviation. So here we have this the heat flexibility and the heat capacity that has been stated as a very mature measure to give flexibility to a market. Next, we have the PV generation units, and of course, as a similar class, the solar heater. The power output differs from the size of the plant and the relative sun position, which changes over day and is also depending on the geometry of the power plant. And we also implemented some simple weather forecasting. We have a weather factor, which is randomly numbered between 0.6 and 0.8 for one scenario. And in another cloudy day scenario, we have a lower weather factor, which leads to lower power outputs from the PV plant. Next, we have the EV charging station, and it is, as explained before, reservation-based. The pricing for the forecasting has or its input values is the ratio from the average to the maximum power that can be charged. So the average power is calculated if we would charge the EV to 100% within the time that we're given from the reservation. This is the average power that would be needed. And then maximum power is, of course, the maximum power that the charger can provide. So on the bottom, you can see a bidding price that corresponds with a charging interval on the top. And we altered the compensation mechanism during the simulations. In the first two simulations, we took a fixed compensation. So the state of charge baseline was if there were unmatched bits, they were completely bought from the outside trader. And on the other side, we made a more flexible approach in simulation C and D. So there have been, again, two different scenarios for that. As explained, the market agents contain various entities. And for the scenario, we defined some entities for each of the organizations to have a more mature scenario. For example, on the left side, we have the neighbors. So these are always houses with different additional entities, for example, EVs or PV plants. Next, we have a local business, which contains several electric vehicle charging stations and batteries. Also, a cogeneration unit and a community PV plant is installed. From Fortiss side, we another participant of the market was this heat and cold storage, who had charging intervals and discharging intervals where it offered energy to the market or demanded electricity from the market. And next we have the TUM office, which also took part in the market, and it was based on a forecasting of the presents probability. So how likely is it that the guys or that the students and Christian, Lars, and so on are in the office, and how much will they then use energy? How much energy will they use then? Yes, exactly. As explained before, we did different simulation runs. So simulation A and B had a strict EV charging regime, and simulation C and D had the more mature fluctuating V stuff. And during the first simulation of 3 days, simulation A, we saw that that the patterns are repeating. So we decided to go with single day simulations for simulation B up to D. So here we can see again that we varied the weather conditions during the simulation and the electric vehicle charger behavior. So here we compensate 100% of the SOC baseline, and in the later scenarios we only compensate flexible or increasing share. So now we have this short demo where a market is, or where the Framatome virtual entities are running. Of course, we have the startup of the physical models and then the processing. Afterwards, the market or the entity gets the clearing. Of course, this is only a shortened video. It would take always 15 minutes that to do one processing and stuff, processing and clearing and so on stuff, because of course the market handles everything only in 15 minutes in intervals. So this is a little bit sped up. And then we have the forecasting of the physical models with the knowledge of the clearing and the prepared offers from the entities which are posted to the market. And then we have the processing again and the logging. And this goes on. We have a processing, sorry, and again clearing, forecasting, and so on. Sorry, bidding, processing, logging, and so on. Yeah, always the same. Yeah. So yes, this takes then place every 15 minutes. Okay, after the simulation run, we have then a result. Here we have the development over the clearing times. We only consider electricity in these plots, and it is the simulation D. So we have a weather we have a sunny weather, and the flexible electric vehicle compensation. Thanks, Lars, for plotting this video. Yeah. Okay. On the left side, on the top, we have this Sankey diagram, which shows the power flows from the units to the other units. And besides this, we have, yeah, of course, the volume per clearing and the price of the clearing. And here is a PV generation stuff. Sorry, I was expecting some additional information here. Okay, as you can see, we now ran through the during the day interval, and we saw that there is a small CHP plant production only, and a high PV generation. During this interval, the batteries will be charged, and we have rather high, low prices, and especially during this interval, we have a high volume per clearing. So hopefully now it works a little bit better. No, sorry, next slide. Okay, during the evening, we have a low production and high prices, and the share of the CHP plant is increasing. So yeah, the CHP plant is a supplier, and the batteries are also still suppliers, but their share is decreasing because the batteries will be emptier, and then their prices, their supply prices are increasing. Next, during the night, we only have the CHP as a supplier, leading to high prices. Of course, nothing happens, so there is a low volume of market via trading, and there is no PV production at all. I will skip a little bit of this because yeah, nothing happens here. And in the end, we also have again a battery as a supplier because there is a peak price, and then the battery price is accepted again. Next, during the morning, or last but not least, during the morning, we again have a PV production. Still some, the CHP also provides some energy, but it is decreasing as the PV comes into its place. And the price are not decreasing immediately because the CHP still provides some energy at a rather high price. Okay, what is the outcome from this simulation? First, we had the idea to create some value for the autonomy for the market participants, because they can use the resources commonly. Yes, as we can see on the table on the bottom, during the sunny scenarios, which are simulation A and D, we have, of course, higher degrees of autonomy, and the sun in general had a greater influence on the electricity than on the heat autonomy. As you can see, the autonomies on the heat market are similar for all 4 scenarios, but on the electricity market, simulation B and C have a minor autonomy because they were the cloudy scenarios. And what is also remarkable, the CHP covers the PV lag partially, as can be seen on the workload. The workload is increasing, or is higher for the cloudy scenarios. Yeah, so the market regulates or controls the resources automatically. Yeah, this is very cool. And another idea or another target was the peak reduction. So the idea was to have cross-commodities and flexibilities to create a value for this peak reduction, of course. We compared our market scenarios, which are in this first row here. We compared the peak powers with several standalone scenarios that happened without the market. I will not talk very much about this, but in general, PP means here peak power, and OC means own consumption. So with the peak power optimized EV charging behavior and peak power optimized battery scenario, we derived the most competitive peak power reduction for the standalone markets or for the standalone participants. But with the market, we could even get a much better peak reduction. Yes, I think that's it from my side. I loved this work. I loved to work with you, decent colleagues. Thanks for the great time that I had during this research project, and thanks for the attention. Yeah.
Thank you very much, Joseph. And yeah, so it's also from an inside perspective impressive to see, because you only see the top of the iceberg, and there are so many considerations and so on we had in the meetings about that. So yeah, very nice and very good presentation as well. So that brings us to the last part. And the last part is about results of dissemination and communication. And I want to give a brief overview on exactly these topics. So when I remember back on the first meeting where Fabio Lenz now also participated, we had a discussion on the website, and the website was a major tool to communicate what we did in the project. And when one looks at the website, it's also a very good timeline of activities that we had, because we tried really to put the activities in there with short reports, and that worked out quite nicely. And the website will also remain, and we'll also put the final workshop on it, so that in the future people can have a look at what was happening in the project. So dissemination events. So we had a lot of dissemination events in the project time. So these are only the external ones. In addition to that, there are also lots of internal dissemination events that I just did not list on the slide. And yeah, so it's just nice to see that the project did give presence at various events to different directions, which also shows the integrative character of the project, that looking at this smart energy sharing neighborhoods is nothing isolated in the energy domain or in the specific energy IT domain, but it's covering so many aspects, because we're covering so many sensors and actuators, business models, and so on. A similar picture is on the research side. So there are also numerous research publications, but emerged from the project. And something that is especially to be mentioned from my side is that we have also lots of publications between the project partners, which is also not always the case. So this also shows that we had a very good collaboration in between the project partners. So next slide is on the dissemination by the industry partners. So there I just put the major points now. So from a Framatome side, a focus, as we heard it already, is on first and second life battery storages, where competencies were extended and things were developed, as we've seen. From Enerim side, the focus was also on improving the products, of course, and so for them it was also very insightful to get, as Jan was also presenting, to get some more insights on the cross-commodity energy sharing and to develop this also within this project. For Wirepas, it's also about improved products. So there, the product, which is a communication solution, was a product that was extended. So a protocol for unsecure and unprovisioned devices that have the right for configuration and security credentials provisioning from backend servers was developed, and it's also part of the product now. Plus, it was interesting also to, through the project, get in contact with the regulations and so on in the German market, where Wirepas is and was also very active. And finally, for IBDM, there was also improvement of the products. So there's now, as described here, a protocol via an API for transferring data into an energy management system, where customers now have a lot of more information because we needed such information for the project, and therefore it became also part of the product. I'm sure that the companies will also be happy to detail that more later in case this is interesting. From the research side, there the Fortiss and VTT are continuously doing technology transfer to the industry, and so one of the initiatives is Smart Mittelstand. Also, results of the project are used now to improve the German economy by giving technological advance to the small and medium companies. There is also research that started in the project, also with partners that were not part of the project, but that we get linked to through the project, that is also going to continue. And as we heard multiple times, as the consortium was really nice, I'm confident that there will be also more research in the future. We are also actively looking for follow-up funding for quite a while now in different contexts. And so yeah, I'm also looking forward to hopefully start something with the consortium in the future. On the teaching side, there was also lots of activities. There was more than 30 theses in the context of the project. The project became part of the continuous teaching activities of different partners, speaking for TUM, for us definitely. And as such, it's also part of the education of young workforce now, which pushes young engineers into the market, which goes into the direction of these smart energy sharing neighborhoods, which is something that will be even more important in the future. Good. So we did not end there. We even thought about, okay, what could be a roadmap of the DECent project? What could be a roadmap of the project results? And here we see a roadmap. We could divide it into 3 parts. So demand-side management, sector integration, and services. And here we see that for 2022, we prospect that tools and solutions for demand-side management in industrial sites will be available 2025, then also in the residential sector, and maybe 2030 the neighborhood and city level. So what we also looked at in the project. For the sector integration, then we have enabling technologies in different maturity levels like the heat pumps and so on. And this will develop further, will become available. So then in the second step, 2025 on, we have economic feasibility of such small scale plants. And in 2030, we might end up at what we looked at in the project, namely increased shares of sector coupling at the neighborhood level. And finally, for the services, 2022, we have showcases of shared ownership of energy resources. Then in 2025, we might have real market pilots. And in 2030, this might become something that is the common standard in different areas of the world, which would be desirable for the good effects that we have seen in the demonstration. In the project, we identified five directions that we looked for finding these insights, which is given on the top right. So the market mechanisms in energy trading, the IoT, Internet of Things, and wireless technologies, blockchain security as base for such a solution, because without this security, it cannot fly. You cannot really provision it because it's a critical infrastructure we're looking at, and active consumers. We looked at what are benefits for different stakeholders, starting from the neighborhood and energy community. A benefit is reduced costs, revenues from participating in flexibility management, improved possibility to impact on sustainability. So the expected ones, but it's still good to see that the project confirmed that it really goes in that direction. For the building users and community participants, it's a better well-being, better indoor air quality, improved possibility to impact on sustainability. So again, sustainability, but also comfort that can be offered as a product. For the building owner, we have reduced costs over building life cycle, sustainability labeling, substantial savings in energy and energy management. For the TSO, DSO grid operators, we have possible reduced investment and operational costs because not so much energy has to be transported and can be used locally. We can have a more robust power grid for the same reasons, because the stability, if we have it locally, do not depend so much on the outside stability. And finally, for the retailer and aggregator, we have revenue from trading flexibilities in the market, lower costs via better imbalance management. So yeah, also what we wanted to see, and so what we also looked at in the project. Good. So yeah, that is the last slide I wanted to show. Yeah, so maybe I do it now. So also, as you already did, so it was a great pleasure being in the project, working with all the actors in the project. We had a very nice journey. We discovered many more things than we expected at the beginning. So to me, the project was very, very nice and very successful to participate. So yeah, thanks to everybody. What are the questions? So this is now the part where especially questions can be asked, even though, of course, all the time they could have been asked already. Do we have questions? And which ones? So also thanks to the audience, because we stayed in time, but still 2.5 hours is quite a lot of work. Does someone have additional comments, want to give additional comments to the project, to the official project closing right now?
Yeah, thanks everybody. Also from my part, it was really fun project, and we had really nice cooperation. Sometimes in this type of smaller projects, the cooperation can be even better than in larger ones. I think definitely here we had a really nice cooperation. Of course, COVID situation made it a bit more difficult in the later part of the project, but we did, I think, nice job with remote meetings and trying to handle the situation. And let's start planning future projects. I think we have a meeting on Friday, so look forward to continue with you guys also in the future.
Very good.
Also from Fortiss side. Yeah, just go ahead.
Interesting project. I must say that I have learned a lot of things which I have no clue of beforehand. So this is really pretty eye-opening project for me. Thank you.
Also on behalf of Fortiss, it was very much fun working with you, doing research, and also getting to know different cultures, especially working with the Finnish side. I think aside from the results we achieved in the research project, I think also the social contacts we had and what we learned about also research in other countries was very helpful, and let's see it as a fertilizer for future research and projects like this. Enjoyed it a lot. Thanks.
Very good. All right. Then, yeah, thank you, everybody. We can clap ourselves the end. So today's meeting really showed that the project made a really strong impact, not only for the participating companies and organizations, but way beyond. And so, yeah, very good. Thank you very much, everybody, and I think we're all looking forward to starting maybe something in the future, also with the Projektträger naturally. So yeah, thank you very much, everybody. Have a great day, and yeah, looking forward to the next endeavors. See you.